In my last class, I had seen Cauchy Goursat Theorem in complex analysis. In my last class, I had seen Cauchy Goursat Theorem allows to find complex integration quickly. And the statement of Cauchy Goursat Theorem is, here the domain is, necessary condition is, I had seen the necessary condition of Cauchy Goursat Theorem is domain is simply connected. And simply connected means, in my previous video I have seen, if this is the domain D, then if we draw any closed curve, this is can be shrink to a point without passing out the region. That means by decreasing, such type of decreasing, this is reduces to a shrink to a point without passing out the region. And this type of region is called simply connected domain. And this is true for any closed curve in this domain. That means in this domain, if we draw any closed curve, then we can shrink this closed curve to a point but without passing out this region. Then this type of domain is called simply connected domain. If we consider this type of domain, we all of us know this is called in art to analyze. So, if we consider this type of curve in this domain, where if we shrink this curve to a point, since here the domain, here consider this part is analytic and this part not be analytic, means consider there exists an hole. If we shrink this curve to a point, then this is does not belongs to this region, this is belongs to this region. So this curve not be simply connected. I hope my all viewers have understood why this is not simply connected. That means I had seen in my previous video, simply connected means there exists no holes. Since here there exists hole, so if we consider this type of curve, since there is hole, but if we shrink this curve to a point, then this would be belongs to in this hole, but this hole does not belongs to in domain, so this is not be simply connected. And sufficient condition of Cauchy Goursat Theorem is, this is the sufficient condition, fz is analytic, then integration over c fz dz equal to 0, where obviously this c is closed contour in the domain D. I hope my all viewers have understood. In my previous video I had seen there exist many functions whose integration on the closed contour is in the domain is 0, but function not be analytic. So this is the sufficient condition. And in my previous video I had seen, when Cauchy Goursat Theorem not applicable, then how we will solve any complex integration when the Cauchy Goursat Theorem not be applicable. And today's goal of this lecture, Cauchy Goursat Theorem can also be generalized to multiple connected domain. And what is the multiple connected domain? A domain that is not simply connected. This is called multiple connected. That means in this picture, since there exists hole, so this is the multiple connected domain. Since multiple connected means when this is not simply connected. That means simply connected. This concept is very important. So I will say two examples to understand the simply connected in better way. In R3, consider the domain R3 minus omitted z-axis. Is this domain is simply connected? No, because here z-axis be omitted. If we consider any curve here, if we shrink, then if we shrink this curve, then always it intersects the z-axis. So R3 minus z-axis, this is not be simply connected, but R3 omitted only singleton set 0. This is simply connected because here I have omitted only singleton set 0. In R3, if we consider this type of curve, then if we shrink the curve, then always it go away from the singleton set 0. But if we consider R2 minus singleton set 0, then it is not simply connected, because when R2 minus singleton set 0, then if we any curve around the 0, if we shrink the curve to a point, then always it intersect the point 0. So R2 minus 0 is not simply connected, but R3 minus 0, this is simply connected, because in R3 any curve containing 0, if we shrink the curve to a point, then this is always be go away from the point 0. So this is simply connected. I hope my all viewers have understood. Now I will see this region and consider this region and this region. In this region, the function not be analytic. Also in the outside of this region, the function not be analytic. But inside this region, the function be analytic. And this domain is not simply connected. This type of domain is multiple connected. Because here, consider this is like a hole. Here the function not be analytic, only analytic inside this domain without this hole. And today's goal of this lecture, now I will see how any multiple connected domain reduces to simply connected domain. Okay? Let's see. Now consider the closed curve C1 and C2, where C1 goes around the whole C2. Obviously, this is the whole. Obviously, this is the multiple connected domain. This is the multiple connected domain because only this region function is analytic. Here function not be analytic. So this is the whole. So this is the multiple connected domain. Now I will see how the multiple connected domain reduces to simply connected domain. For this, if we cut the annulus, this annulus, we all of us know this picture is the known as annulus. If we cut the annulus by this type of path and the original path considered in this way, and the original path cannot get back to the starting point without taking a detour C3 around the new path described as, then the path reduces would be such type cut in this two way, because if we not consider detour or consider this path as C3, detour of C3, then we cannot get back to the starting point. Now notice the new path is described as, consider new path as C, new path described as C1 plus C3. Here C1 plus C3 and C2, notice the orientation would be back. So this is minus C2, and since by this way this is go back here, so this is also minus C3. And notice now this is reduces to closed simply contour. I hope my all viewers have understood how multiple connected domain reduces to simply connected domain. Okay. And notice in this region Fz is analytic inside this closed curve, where this closed curve is simply closed contour. Then by Cauchy Goursat theorem, integration around this closed curve Fz dz equal to integration Fz dz by this closed curve C1 plus C3 minus C2 minus C3 equal to 0. And we can separately integrate this as Fz dz around C1 plus Fz dz around C3 minus integration Fz dz around C2 minus integration Fz dz around C3 equal to 0. And notice the path. Here this part and this part would be cancelled. That means that imply integration Fz dz around C1 equal to integration Fz dz around C2. That means from this we can conclude that let Fz be analytic in a region who is bounded by two simple closed curves C1 and C2 on these curves. Then integration Fz dz along C1 equal to integration Fz dz along C2, where the orientation of C1 and C2 are same. I hope my all viewers have understood how multiple connected domain reduces simply connected domain. And generalization of this above result is, let fz be analytic in a region bounded by non-overlapping simple closed curve C, C1, C2 up to Cn, where these C, C1, C2 up to Cn are inside this C above in this figure below, and function is analytic in this region. So by this above result we can connected C1, C2, C3, C4 by this previous result by a path. Then this multiple connected domain would be reduces in simply connected domain. Then by this above result we can write fz dz along the contour C, whole contour C, equal to fz dz along C1 plus fz dz along C2 up to fz dz along Cn. This is the result of above result. Now let's say one example. Consider as for example C is a simple closed curve enclosed in z equal to 0 and z equal to 1. Then what is the value of integration 1 over z times z minus 1 dz? We can write 1 over z times z minus 1 as 1 over z minus 1 over z. Here this is the multiple region because this is the hole around the point 0 and this is another hole around the point 1. Now by this theorem integration cfz dz equal to summation I equal to 1 to n integration ci fz dz. So by this theorem we can write integration 1 over z minus 1 dz minus integration 1 over z dz with respect to, consider this is C1 curve with this orientation and this is C2 curve with this orientation. With respect to C1 curve, here also C1 curve plus 1 over z minus 1 dz with respect to C2 curve plus 1 over z minus 1 dz with respect, sorry here minus 1 over z dz with respect to C2 curve. By this theorem we can write this as C1 means the closed curve around the point 0. So we all of us know if C is closed contour for which z0 is an interior point and n is positive integer, in my previous video I had seen integration dz over z minus z0 to the power n, this type of integration would be, the value would be 2 pi I when n equal to 1 and when n greater than equal to 2 then this value would be 0. I had seen in my previous video here z0 is the interior point, when z0 would be interior point. Notice C1 means here the closed curve around the point 0 and in this region this function is analytic. So by Cauchy Goursat theorem we can tell this value is 0 and in these curves closed curve C1, in this closed curve C1 since it has a singularity at the point 0, so this value would be, we all of us know this value, in my previous video I had seen this value is 2 pi I when it has a singularity. C2 means the closed curve around the point 1. So around C2 it has a singularity, means it at the point 1 the function is not defined and here would be, this value would be, since n equal to 1, so this value would be 2 pi I, this value 2 pi I, and in this curve this function is analytic, so by Cauchy Goursat theorem we can tell this value would be 0. I hope my all viewers have understood why I have told you Cauchy Goursat theorem allows to find complex integration quickly. Since by Cauchy Goursat theorem we can tell this value, this type of function, the value of the integration would be 0. Since we are know the Cauchy Goursat theorem, so by this theorem we can tell this value would be 0 without calculating. Okay. So the value of integration actually would be 0. I hope my all viewers have understood this is. Similar type of example, dz over z square plus 1 around the curve mod z equal to 4. And z square plus 1 means z plus I, z minus I. Around the point z equal to 4, there exists two singularity at the point I and at the point minus I. So consider two closed curve around the point I and around the point minus I. So this is the multiple connected domain. Therefore dz over z square plus 1, we can write this as 1 over 2I integration over c 1 over z minus I minus 1 over z plus I dz. We can write z square plus 1 as such type. Now by the theorem, above theorem of multiple connected domain, 1 of dz over z square plus 1, here region z equal to mod z equal to 4. We can write this is as 1 over 2I integration along this contour C1 1 over z minus I minus 1 over z plus I dz plus 1 over 2I integration along this contour C2 1 over z minus I minus 1 over z plus I dz. And in C1 the value of this value is 2 pi I, and since in C1 this function is analytic, so this value would be 0. So that means in this value is 1 over 2I times 2 pi I, and in C2 this value is equal to 0 and this value is 2 pi I. That means this value is just common 1 over 2I minus 2 pi I. So this value is 1 over 2I times 2 pi I minus 2 pi I. This value is equal to 0. I hope my all viewers have understood this type of example clearly. How we have to solve any complex integration in multiple connected domain. Okay? Well, today I will stop here. In my next video, I will discuss different type of complex integration is another method. But at first I will highly recommend you please see today's video with pay attention, because this type of concept actually very important for higher study. Okay? See you soon. Stay safe and stay positive always, and don't forget to subscribe my channel for more videos. Thank you so much.